A well counter detects and measures gamma photons emitted by a radioactive sample. Let's follow one photon through the detector. The sample is placed inside a deep well in the sodium iodine crystal. Because the crystal surrounds the sample, a large proportion of the emitted photons enter the detector. When the photon enters the crystal, it continues until it interacts with an atom. The location and type of the interaction are probabilistic. During photoelectric absorption, the incident photon disappears and transfers all of its energy to an inner shell electron. The electron is ejected as the photoelectron and deposits its kinetic energy in the crystal. The inner shell vacancy is filled by an outer shell electron. This produces a characteristic X-ray, which is usually reabsorbed nearby. In the Compton interaction, a photon transfers only part of its energy to an electron. The recoil electron deposits its energy in the crystal, while the scattered photon may escape or undergo another interaction. The energetic electrons produce many ionizations and excitations along their path. This energy migrates through the crystal to the thallium activator sites. As the activator atoms return to ground state, they emit visible scintillation photons. The amount of light produced is proportional to the energy deposited in the crystal. The scintillation photons travel through the optical window and strike the photocathode. Through photoelectric effect, the photocathode releases electrons. Focusing electrodes direct these electrons towards the first dynode. Each dynode then releases several secondary electrons, creating an increasingly large electron cascade. The amplified charge is finally collected at the anode. After leaving the anode, the very weak signal is sent to the preamplifier. Inside the preamplifier, it's assigned a voltage, and it is shaped somewhat and prepared for the amplifier. Within the amplifier, that signal is really amplified and the pulse is shaped to prepare it for the pulse height analyzer. At the point that it leaves the amplifier, that pulse is proportional to the incoming original photon energy. The collected charge produces a voltage pulse. The height of that pulse is proportional to the energy originally deposited in the crystal. The pulse height analyzer measures the amplitude of each pulse and assigns it to an energy channel. Some pulses enter lower energy channels, while larger pulses enter high energy channels. As many events are recorded, the channel counts form an energy spectrum. Compton interactions contribute to the lower continuum, while full energy events contribute to the photopeak. The complete signal chain begins with a gamma photon depositing energy into the crystal. That energy becomes scintillation light, then multiplied charge in the photomultiplier tube, and finally a voltage pulse. The pulse height analyzer assigns the pulse to an energy channel, adding one count to the measured spectrum.